Thank you very much. I'm Wilson Ho. Thank you for participating in this webinar. I'm going to explain the key items in the videos from a perspective or practicing engineer. It would divide into two parts. The first part is the background knowledge, and then we would the case sharing, the case just shown in the video. We will present much more information for the case. For the background information, I would talk about the noise reduction performance of retrofit damper. And then there is two types of damper from the mounting design. One type is called resilient mounting or profile mounting. The other type is called rigid contact mounting. The idea is totally different. Most damper in the world are resilient mounting. The third, we are going to talk about the noise reduction performance against the check decay rate and fastener stiffness. Because lower fastener stiffness, softer force fastener would have higher noise reduction performance of the wheel damper. And then we will talk about the noise reduction performance according to TSI noise limit. This is different. I did not see people compare the noise reduction performance of damper against the absolute noise limit. So I try to do that. This is where not many people doing that, because all the previous study is focused on the relative level. But if we want to see the absolute level, how it will improve the overall performance, making the entire wheel system being quieter. After the background information, I would provide more information regarding the case just shown in the video, damper reduction of 10 dBA. I put a question mark there because I know some people may not agree it is 10 dB. Some people say that it is more than 10 dB, and some people say that it's less than 10 dB. So hope you can make your wheel angle. Okay, we can see there is many different type of wheel damper. Some of them is not included here. However, there is a general impression that the wheel damper only provide 2 or 3 dB noise reduction. For example, in this paper, it just I just randomly select from the internet. It is published in December 2017. It also refers the previous study. The wheel damper performance is 3 to 7, sometimes 3, sometimes 7 dB noise reduction, but mostly around 3 dBA. If they look at the different type of wheel damper, different type 1, 2, 3, 4, 5 different type of wheel damper, sometimes they can produce 3 dB, sometimes produce 2 dB, and many times produce 1 dB. One of the worst one is provide 0 dB. So the average of different type is 2 or 1. If we look at different type of train, is around 2 or 3 dB. So your impression of 2 or 3 dB is correct according to the literature. Okay, why they are not so good? Because I think one of the reasons is that the mounting of wheel damper is not very good. The damper design can achieve much better performance than the design. So maybe 6 dB or 10 dB. However, in the site on-site result, it always produce 3 dB. So I think rusted surface or the convex markings affect the damper conductivity and then affect the noise reduction performance. This type of convex marking on the wheel is very common. So when the mounting damper on this type of wheel, the conductivity is significantly reduced and the damper performance is reduced. From the wheel angle of how to mount the damper on the railway, we can divide the damper into 2 different types. The first type is resilient mounting or profile contact mounting. We can see that all the damper is trying to have a curved surface to fit to the wheel surface. So how to match the damper to the wheel is very important. However, in the retrofit situation, it's very difficult to get a perfect matching. So the damper performance may be affected by the mounting connectivity. This type of damper, the design aim is to maximize the interface contact area. One of the design aim is maximize the contact area. On the other hand, there is a rigid contact wheel damper. Our company take research on this type of damper for more than 10 years. You do not see the rubber. You do not see the rubber. Everything is metal to metal connection. Actually, there is a very, very small layer of rubber. The small layer of rubber is in between. This is 1 millimeter thick rubber aligned in perpendicular direction. All the flat surface between this have a rubber layer. So in this one, we have 1, 2, 3, 4, 5, 6, 7, 8, total of 8 rubber layer. But from the outlook, we only can see the metal. It's different from the other type. They have some resilient material on the outside. Okay, the design is totally different. The design aim is maximize the connection. That means maximize the connection force, i.e. the damping force, because whatever damping force generated from the damper, generated by the damper, need to have a very good contact in order to transmit the damping force into the railway. Okay, this is the one of the graph showing the different type of rail damper, the performance. The x-axis is the check decay rate. The y-axis is the noise reduction. We can see that in general, noise reduction is much better at this location. That means when the check decay rate is low. A low check decay rate has higher performance. Low check decay rate means that the fastener system provide less damping. Because the original fastener system provide less damping, the rail have higher mobility and higher vibration level would be excited by the string bypass. So actually the rail have higher vibration, then if we add the damper is more effective. So everybody agree that when the lower the check decay rate have higher reduction, but actually not meaning the noise level is lower, just meaning the noise level before applying damper is higher. All the circular dots are those profile damper. The profile damper achievement is 1 dB, 2 dB, 3 dB. The triangle one is the half installation of the rigid contact damper. We can see that by half installations, in some cases, it already achieved 7 dB. 4 or 5 dB is very common. So we believe the mounting is the major difference between whether a damper is good or not good. So I may not able to more detail explain this graph. So if you have questions, it's welcome. Okay, talking about the check decay rate. Lower check decay rate, that means the fastener is soft, has lower stiffness. There is different type of fastener. There is direct fixations, ballast check, different type of base plate, many different type of base plate. Basically, this is very rigid. This is relatively soft. Normally, the railway would be designed in this range, 20 to 50, the stiffness. Some of them try to make a very soft fastener system, such as floating slab or this type of fastener system. They may provide around 10 kilonewton per millimeter. So this is making the rail very soft, such that when the train running on it, the vibration would not transmit into the structure. So this is basically for control of ground bore noise. Control of ground bore noise. When they want to control of the ground bore noise, the energy in the rails will be stay within the rail. They would not allow to transmit into the structure. So that the vibration energy stay in the rail and making the rail have higher vibration. When the rail have higher vibration, when we apply the damper, have higher reduction. So in certain case, reduction of 15 dB is achievable. From the experience in Hong Kong, I divided this table. In Hong Kong, the fastener type would divide into 4 types: direct fixations, medium attenuation base plate, high resilient base plate, isolated slab track, and floating slab track. And the corresponding noise reduction of damper is there. And sometimes it would be better than this, depending on how noise of the rail. If the rail is more roughless, then they produce higher noise level. When damper applied, it would produce higher reduction. All this is talking about the relative. The damper performance is depending on how noise of the original rail without damper. That is relative. If we want to really help the railway industry to provide a quiet surface, we need to make sure it achieves a quiet train surface better than the requirement. The technical specification for interoperabilities by the European Union define the noise limit for a train. When measured at 7.5 meter at train speed of 80 kph, the noise level should not be higher than 80 dBA. So all the new trains in the past 5 years, they achieved this noise level. So whether our damper can bring down this value, from our experience, we can easily bring down to 74 to 77, subject to what type of fastener system. In some case, we make it down below 70, 67, 68. But in general, I would say 74 to 77. The best case was 66. So depending on the fastener system, because resilient fastener system, resilient track form, produce higher noise level and produce higher performance of noise of the wheel damper. Okay, if we look at the absolute levels, TSI limit is 80 dB. With the damper, we can generally achieve in the green line. So although the reduction on this side is much higher, it could be 10 dB or 15 dB, but the final level is almost a constant. Whatever track form type, we can achieve similar noise level from the train. Okay, then talk about the case sharing. I just finished the part on the background information. I'm sorry that I'm going through that part quite quickly because I want to have more time for discussion on the case. The case is a building adjacent to the rail track, 20 meter away from the track. We put a microphone there and install 80 meter of rail damper. Then we see what is the noise reduction by the rail damper. The distance from the rear track is 30 meter. From the far track is around 50 meter. From the far track, actually, the parapet wall is partially screening the noise. So the far track the noise level is already very low. We put 80 meter rail damper there. It is half installation. We will explain what does half installation mean. And low damper on the far rail. We put our microphones in the balcony, weather microphone for 24 hours for 5.5 years. We just removed the microphone 1 or 2 months ago. This is the data obtained in the microphone, from the microphone. The time history. Whenever there is a train passing through the measurement point, it increased the noise level by 10 dB, 15, 20, or even 25 dB. We can see that there is 3 types of train pass by. The black line representing the train pass by at the rear track, The red line represents the far track because it's further away and screened by the parapet. And the gray line is the double pass by. The moment have both rear track and far track train passing the measurement point at the same time. We can see that the rear track is around 15 dB or 10 dB higher noise level than the far track. The rear track here, far track here, around 15 dB difference. We only install damper on the rear track to see whether we could bring down this level. If we can bring down 10 dB, it's still higher than the far track. So we need to achieve more than 10 dB in order to make the rear track and far track have similar level. So then we are going to have a 5-year monitoring, and we want to get non-biased data. We want to have single data for each week. So how we obtain the data? Normally we take 5 day or first day, and then take half-hour data in the early morning from 6:30 to 7 a.m. in the morning, 6:30 to 7 in the morning. Then we select all the rear track train pass by, all the rear track trains. So in this case, it's 1, 2, 3, 4, 5, 6, 7. So we have 7 train pass by within this time period. We take average of these 7 trains. Let's see the spectrum. Actually, the spectrum is already very consistent, have a noise peak at 630 due to the corrugation. And then we average these 7 trains to obtain a single data. So after obtaining a single data, we compare the data every week. If we require, we will compare every day. So this is the noise level before installing the rail damper. We can see that there is the noise variation around 4 or 5 dB. It increase and then decrease. The increase is due to the corrugation growth, the development of corrugation on the whale surface. If a appropriate grinding, it will bring down the noise level. It's a very good grinding, it may bring down further. So before we install the whale damper, we want to see how quiet could be a whale. If we make a very, very smooth surface, we make a special maintenance for the whale. So we want to see if we try our best, how much noise reduction by just make a better whale, just better surface. So we already see that this is already being done around 4 dB, depending on how we compare, maybe 5 dB, maybe 3 dB, 3 to 5 dB, we just make a better smooth whale. We're using whale milling. They have the milling machine and then with longitudinal grinding to make a very, very smooth surface. This is also show the entire monitoring period. We start the monitoring in May 2017. In June 2018, we make a very smooth whale to see how much noise reduction by just making a very smooth whale. Then we monitoring the noise level after that. Of course, this special treatment on the whale is not regularly used. So normal grinding would be as normal during the operation. So actually, this type of smoothing, it makes the whale surface very smooth and better than the TSI roughness limit. We take the roughness measurements just before the whale damper install. We found that this is the TSI limit. It is better, much better than the TSI limit in the critical range from 500 Hz to 2000 Hz. This is the critical area. 3 dB better than the TSI, or at some location is 10 dB better than the TSI. This is very difficult to achieve. Just as a reminder, TSI target roughness is established for the noise condition test of a new train. So actually, it's not for the operation whale. Operation whale is very difficult to achieve this type of smoothness. Generally, TSI target is not applicable for the operation whale because it requires extensive whale maintenance. Actually, just 2 or 3 weeks later, the roughness will go higher than the TSI limit. Okay, then we install the damper. We install at 2 lights. Install first 1 light, then waiting another 4 days, and then install another. So in the first light, we install the whale damper in 1 whale. Then we install another whale. By install 1 whale, it already have around 2 or 3 dB noise reduction. This is by installation of damper on 1 whale. There is no damper on this whale. 2 dB reduction. And then we will install the damper on this whale as well. So this is a half installation. What I mean half installation is this is damper, low damper at this space, damper, and no damper in this space. If required, we can also put damper on this space. This track is using a high resilient base plate. Not sure, it's some kind of very high resilient whale. It is the UIC60 whale, have a courage of 2,000 meter, damper installation of 80 meter of the track, half installations. We can tune the oscillation mass of each circular metal ball. We tune multiple frequencies, covering 500 to 1,000. The train speed is around 70 kph. This metal mounting rigid contact whale damper, they have very rigid mounting the plate onto the whale. This is the mounting plate. Then there is 2 rubber layers, and at both sides of the mounting plate, allowing the oscillator to respond to the vibration. Whatever vibration, it will counteract oscillation. It will produce oscillation counteracting the whale vibration. So it produces very strong damping force. Okay, come back to the roughness. We have only 2 opportunities to measure the roughness in this whale. During the whale damper installation, we also take the roughness measurement, and it's still very good, a little bit better than the TSI limit. But we can see that just 2 weeks, the roughness is already increased 2 or 3 dB. If 2 weeks increase 2 dB, 10 weeks increase 10 dB, normally the whale grinding would be 1 year. 52 weeks will increase 52 dB. it would be outside the range of this. So the corrugation growth is the major problem in this case. Okay, so the whale damper was installed on 5th and 9th of November in 2018. In the far whale, not the far track. All is in the near track, near whale, and near track far whale. Okay, this is the monitoring results. We already discussed this part before whale damper. Where is the best achievable noise level without damper? Then after install the damper, we monitor another 4 years. So what is the noise level difference? This tool is due to a malfunction of some grinding. It's once they find that they fix it and make it quiet, make the whale surface become normal. This type of malfunction of grinding, it was not uncommon in the past, but nowadays they are improved the maintenance that it is very seldom to have such grinding created noise. For how much noise level reduction by the whale damper? The entire presentation today is talking about how many dB noise reduction from the whale damper. We can say that it is 4 dB reduction, just the average of noise level of that best achievable and the average level of the damper period of 4 years. Please look at this data. Every data is average of 7 chain or 8 chain or 6 chain. So the data itself is consistent, repeatable. So somebody would say that we compare to the average level before any special treatments, then we would say that this is 7 dB noise reduction. Somebody could say that it could be 11 dB noise reduction. I do not agree this, but anyway, somebody can say that this is 11 dB noise reduction. So we can see the spectrum. The spectrum before the whale damper installation, there is a corrugation noise peak at 630 Hz. After the whale damper, we have a very smooth, and it is 11 dB noise reduction. I think this is too optimistic. Okay, come back to look at the noise level. Compare the near track and far track. In the beginning, the near track and far track have 6 or 7 dB difference, 14 dB difference, 15 dB difference, or around 15, 16 dB difference. After the damper installation, the near track level is slightly higher than the far track level, maybe by 1 or 2 dB. And it have the similar pattern even later. It do not change. If we look at the far track data, if we also put the far track noise level data in the graph, we can see that around the damper installation period, the far track noise level do not change. It only variation within 2 dB. However, the near track noise level is from here to there. This is due to the installation of noise barrier at the far track. Okay, let us have an overview on this case. We put a microphone here, and we install 80 meter of track with half installation of whale damper. We got 4 to 11 dB noise reduction at this point. If the microphone at higher locations, the performance would be less, maybe 2 dB or maybe 3 dB. It would be less performance if depending on where we put the microphone. If we put the microphone more close to the whale, it would get better result. Also, if the damper install extends to this area, for example, a 150 meter of track installed with damper, the noise reduction would be higher. Of course, we can also put damper at the empty space. So, but half installation is already satisfied the client. So there, nobody asked me to install more damper at this whale. So if we put more damper, maybe 200 meter, and put the damper there, and put microphone all around the building to see how many dB reduction. That is what I want to know. But of course, I do not have such opportunity. But anyway, by half installation of whale damper for 80 meter track, we are obtaining 4 dB to 11 dB. We expect if we put the damper in the empty space, or the empty space, the energy dissipation would be another 3 dB, around 3 dB. It's very complicated. So I don't know how many dB would be reduced. It could be 4 dB to 14 dB, depending on your view angles. So, but normally, I think both the railway engineers and the EIA specialists, they would like to take 4 dB for some reason. I don't understand. But this is why it is very difficult to promote the real effective mitigation to the industry. This comes to the end of my presentation. Thank you very much. So I hope you enjoyed the presentation, and I'm sorry that I did not explain it well on the background knowledge. Thank you very much.
So now this is our Q&A session now. Please feel free to ask any questions through the microphone. Please note that your microphone is muted by default. Please turn it on if you will have any questions. Thank you.
I saw one question. I have a question on the rail damper locations. It's in Hong Kong.
Hello, Wilson. Can you hear me?
Yes.
Yes. For your last few slides, that you have mentioned that there was 18 meter of damper installed in the rail track. But I think I also realized that the microphone location is not at the middle of the damper, which means this is offset from, which is some area. I want to ask why the microphone is not at the center of the damper location.
Okay. You have a very, very good observation.
Okay. The microphone location is almost the end
the
of
microphone location is because we installed the microphone at this location. It is screened from this side in order to achieve the best performance of the damper. We select the 80 meter to put on this side, mostly on this side. It's around 20 meter on this side and 60 meter on this side. During the waiting of the questions, I have prepared one slide. This is everybody may already know this slide. This is talking about the noise reduction effect or by slower the train speed. Normally, the train speed in a metro system is around 40 to 80 in Hong Kong. In most cases, some of them may be 120. So by noise reduction, by reducing the train speed, it is at most 5 or 6 dB, because anything lower than 40 is not worth to further reduce. Sorry, the red line is the overall noise level of the train. It is the total level of 3 components: the rolling noise, the traction noise or motor noise, and the aerodynamic noise. So we can only reduce the noise level of the rolling noise. So if we totally eliminate the rolling noise, assume the damper have infinitive damping, no noise from the rolling, then the noise level would the summation of these two lines. So we can see that it is quite difficult to achieve better than 10 dB noise reduction. It's very difficult because once we reduce the rolling noise by 8 dB, then the noise level from other source, such as aerodynamic force or the traction force, traction noise would be dominant. Also, there is 2 equations. The speed dependent is 20 knot or 30 knot. Both are correct. 30 knot is the instantaneous noise level. However, if we slow down the train, the duration of train pass by is longer. So if we reduce the train speed half, then the duration of pass by is double. So finally, the average noise level, or average over half hour, or the average pass by noise level would be just 20 knot. So for average half hour SPL, it is like this. So 30 dB is equal to 20 dB on this side. Okay, this is the, okay, thank you for your time for me explaining this graph. So Matt, do you receive any questions from the audience?
Yes, Louis Lau asked, how many dampers can be installed overnight for retrofit situation?
In our experience, we would target around 80 to 100 damper for each light, but depending on the man-hour working force, we can install maybe up to 200 per light, depending on how many people doing. In the past, normally we achieve 80 damper per light.
And what kind of maintenance the dampers is required?
Low maintenance. Sometimes we because we use the lug and screw, in the beginning, we have certain concern on whether the lug, whether it will loosen. So we using a torque wrench to make sure it have the same mounting force. But we found that they do not turn. After a few years, we found that this, because we using the nylon nut, it do not turn. So it is very stable. Just one nut is already enough. They do not turn. They do not loosen. However, because the wheel surface have certain gap, once it have certain vibration, those gaps will become large. Then maybe after a few months, we need to tighten the lugs again, because the gap is being loosened by. It's not due to the lug turning. It's due to the gap more compressed. If no more question, we just 1 hour. So thank you for your attendance on this presentation. I hope you can invite more people. And actually, if you have any railway noise, I'm very happy to share my knowledge on this area, because I'm working in the consultants on the railway noise control. I have a feeling that everybody to reduce the noise, but not many body want to have an innovative solution. They want to have those traditional measures, such as noise barrier, because the performance is very reliable. They know that, and also noise barrier from the residential people, they see once you build a noise barrier, they would not complain again. But they are not interested on innovative measure because it do not solve their problem. Okay, thank you very much. I hope you enjoy this webinar, and we have the next one in the February of 8. The railway retrofit measure, damper and grinding. Actually, today we already cover some of it. So in next video, we would present more. We would present an invention, a portable rail grinder. It can be taken into whatever location. It invented because in the pit tram Hong Kong, the rail is very steep, around 25 degrees. So a normal rail damper is not able to do the grinding there. So we invent a grinder for grinding this type of rail. So thank you very much. I hope you enjoy it. This is the end of the presentation.